Just take, I think, a minute. Good evening, all. At the outset, I wish all the students, alumni, and all your family members are very safe at this juncture. I'm very happy to begin the community G-Meet, the Alumni Lecture Series, which is the 25th, the Silver Jubilee Series in this 2021 with the talk from Ms.Anusha Rajagopalan, the 2011 graduate batch. A very quick one-liner summary of her progress is she's a double master's graduate with masters in both chemical engineering area, process engineering, and also an MBA. And she chose to come back to India, and she is in one of a very good consultant firm, or an energy consultant risk analysis firm. And this gives a right platform for all the aspiring graduates, the current students, to know from her what master's degree has, in fact, and how to choose a career from that. With this very small introduction, I welcome all of you to this Silver Jubilee talk in this series. And thanks, Anusha, for accepting our invitation and for gracing us at the Alumni G-Meet and sharing your experience with the current students. I'll stop sharing and you can continue, Anusha. Yeah.
Sure. Thank you so much, sir, for that very, very generous introduction. Thank you everyone for being with us here on this Sunday evening. So as sir mentioned, I'm from the batch of 2011. So, and it's very surreal for me to come back and look at this magazine release happen, because in our batch, when we were in second year, I guess, we started off with a magazine initiative. And at that point of time, when in the third year, fourth year batches ahead of us, there were about 15 or 11 students. So the entire combined class strength of third year and fourth year was lesser than our batch strength. So that was so we were sort of the turning point where the class strength of chemical engineering started increasing. And, as more people, more the enthusiasm, and we guys wanted to start off with a magazine initiative. We started getting sponsors first, and then we managed to pull through one issue of that magazine. I still have a copy somewhere lying in my house. And subsequently, the third year, we went to a competition, IICHE student chapter competition in Bombay. We just got wind of the invitation from a friend, in another chemical engineering department, I think in NIT or somewhere else. And we just thought, hey, let's go do a equipment design competition. And three of us went, and we ended up winning it. We came back with the trophy and all that, and we said, why don't we start an IICHE chapter in our department, right? So then we went through the requirements for what needs to be done, and we were finishing our third year and entering into fourth year, and we couldn't, at least I wasn't fully involved in setting all that up. But I think the trigger was going to that student chapter run symposium and coming back with a trophy. So all this is sort of very surreal to me that it's been 10 years of the student chapter, and I'm coming back as an alumni to share my experiences and whatever little I've learned so far. So yeah, before we begin, I'd like to take a moment to appreciate this. And this is a lot of effort. I actually went through the YouTube stream of the previous G-Meets, and I'm so happy to see we've got alumni in in all sorts of walks of life. We've got someone in Uber, we've got someone managing a plant with a unionized labor, we've got someone doing semiconductor engineering roles in the US. We had an alum talk from the 99 batch. So all of that was so insightful. And I guess I'm going to step on a lot of their content as well. I'm going to be repeating what some of them have already said. But reason why I'm reiterating about those YouTube stream is that it was just a very, very rich content, rich stream of information. Okay, so at any point of time when you don't know what to do, or you don't know who to ask a question at in the middle of the night, just look at that YouTube stream, pick up a talk, you'd most likely get your answer. So with that said, let us quickly start. I'll start sharing my screen. I have a small deck made. I'll,
Yeah.
So can you see it?
I think it is sharing now. Yes. So you can go to PowerPoint mode so that it's slightly bigger. Slideshow mode.
Yeah. So do you see the slideshow yet?
Not yet. I'm not seeing. Anybody else? Are you seeing slide share mode?
No, sir.
Not sure.
Yes, sir.
Okay. Yeah. No, sir. Yes, sir. I'm not sure. What is this?
No, it is not on slide share. The presentation, it's on a screen share mode, not on a slide share mode.
Yes.
Okay.
Okay, but I think.
Okay. I think
yeah.
I think I know what to do. Just give me a minute.
But I think some office has this kind of disturbance, I suppose. So it's okay. So if that is there, what you do is you just remove the side panel and then enlarge the size. It should be okay. You can again share. It is sharing now. Yeah, now it's clear.
Yeah. Okay.
Yes.
Okay. So okay. So quickly moving on. Um, like Professor said, I mean, I think there's enough introduction already, so I'm not going to introduce myself again. So let's. The agenda for today's session is going to be a quick overview of my journey so far. What was my motivation? How did I transition from an undergrad in chemical engineering to a master's in industrial engineering? And what was my first job like? It was I started as a market research analyst in a petrochemical consulting firm, and what did that feel like? And then I'll zoom out a little bit to give a generic big picture overview of oil and gas industry. That actually will tie down to why I did an MBA. So, and what were my takeaways from MBA? And what was the overview? What do I do right now? A quick overview of that, because there's a lot of content and I don't want to jam renewable energy again into this. If you have any questions, we'll take it up at the end of this session. And finally, a few closing remarks and what I want all of you to take away from this session. Okay. So any questions, or if you feel I skipped something, if you feel I went too fast in a particular point, please make a note of it and get back at the end of the session. I think we'd have about 20-30 minutes for discussion easily. So I'd love to hear from you and have a more vibrant Q&A session, right? So okay, so my journey so far started out from Chennai, still in Chennai. So born, raised, Chennai, huge movie fan. Sorry, just streamed quickly. So first step was Sastra from 2007 to 11. And what I call chemical engineering, if I had to give it one line, it would be it taught me how things are made, right? Like the process part of it, how are things manufactured. Then from there, I moved on to Texas A&M University for industrial engineering. And the questions that were answered there were: how much do I manufacture? When do I manufacture? Where do I manufacture? So so you see the connect, right? So the one-liners are to give you a connect between the different my path, my journey path. So after my industrial engineering, I worked for about 4 years in a boutique consulting firm, a small consulting firm in Houston. I did market research and business analysis for chemical companies, both petrochemicals and mining related, like the inorganic chemicals side. And then I came back to India for MBA from Indian School of Business. And MBA is what I call the why of manufacturing. Okay? Like, why do you have to produce something? Like, why do you want to do this in the first place? And after which I've been working, I graduated in 2018 from ISB, and I've been working in KPMG as a energy consultant, as a strategy consultant in the energy sector. So my day-to-day job right now involves helping government utilities, power, like your power distribution companies, in integrating more renewable energy. Okay. So moving on. Why did I pivot to industrial engineering for master's? So I made this slide. I kind of skipped the chemical engineering part, but it comes into this slide. why did I pivot to industrial engineering for masters, right? So I was kind of like this Ross Geller in this picture who is stuck in a staircase. Like he knows he knows he needs to go somewhere, but he's like screaming pivot. Okay, so in third year, I was very clear about what I didn't want in life. I didn't want to be a teacher. I didn't want to be in research. So, like Sir was mentioning before the talk started, I didn't want to be take the traditional academia route, do a master's, do a PhD, do catalyst design, and then sit behind a lab, doing that for life. I didn't see that for myself. But I didn't know what I wanted either. So I was kind of stuck in a place in my third year where I was constantly thinking about what I need to do. So that led to some introspection on what kind of life or what do I want from my life, what do I want from my career. And that's when we had this course called equipment design. I think it should still exist because it's a very, very important course. So what it does is it brings together concepts from your heat transfer, mass transfer, puts everything together and says, design and equipment. The question you get there is design and equipment, given the flow rate, given the size, technical conditions, design the diameter, volume, and draw it as well, right? So that's when I kind of started thinking like, okay, this is how all the different courses come together into designing a plant. And that kind of took a next step when I did a final year project in Sastra paperboards. So that's a paper plant in Erode. And we had the fortune of working with the plant manager there, a really nice person. And he took us on a tour through the entire plant. And what we got to see, we used to go to the office every day, sit in the plant office, and look at what everyone is doing. We were these three clueless fourth year engineering kids who were trying to do who were taking full pride in the fact that we were doing our final year project outside the campus on our own, right? And we'd look at most of the time was spent on looking at what others were doing. So there used to be this plant person who reported to the plant manager. I think he was a mechanical engineer by degree. Every day he would walk in, take a tour of different control units, and then start calling people up at the various control rooms and say, what was your production? So, and he'd get really tensed if production at one unit was lesser. So that led me to thinking, why is this man getting tensed every day? Like, what's wrong if production drops by a few kilotons, few tons a day, right? So then the answer led me to the commercial office. So they said, oh, we have commercial department's targets to meet. We need to make sure the plant produces so much. We can't, and it was not as if the entire plant was super efficient and all that. There were quite a few inefficiencies in that plant. It's a fairly old plant also. So it was not about the equipment design or safety issues. It was more about the commercial department's targets that they were concerned about. So that's when I realized, okay, so the real power in a plant lies with the commercial department, because that's who every engineer is scared of. So who or what determines plant design and output targets? This was the question that led me to industrial engineering. Okay, so I wanted to be someone who had a bigger picture view of the bigger picture. What is really moving and shaking things inside a plant. So other than that, a few takeaways from Shastra. For those who finish these courses, please keep these books intact. For those who are going to do this, please pay attention in class. So ICT, OCT, I don't know if it's still two separate courses or one, inorganic chemical technology and organic chemical technology. These are very unique to chemical engineering because it teaches you how to think about a problem in a process manner. Okay, anything that you give me today, I'll split it and put it into boxes and make a flowchart out of it. Okay, so I don't really remember how paper was made, but I know that if somebody gives me a starting point, I'll put together the puzzle pieces and make a flowchart out of it. So the number of flowcharts you learn in those classes will make you, will enable you to make flowcharts out of anything. Then process calculations, most fundamental of courses in the third sem, and I had a very tough time with it. So I think this was the course that introduced me to using an Indian author textbook to understand a foreign author textbook. Okay. So but then in hindsight, it travels. This process calculations course travels with you throughout your life, okay, in some form or the other. So although you might not be exactly calculating how many moles of this particular compound you need, you will still be using it in some form or the other. then petroleum engineering because I ended up working for petrochemical clients in my first job, and then my final year project at CSI both because it really opened my eyes to how a plant operates. And finally, friends without which we wouldn't have this beautiful picture here, or friends that are still my support or my support system, who've been my support system and who've been more than family now. So now moving on to industrial engineering, right? So what did I learn in industrial engineering? So industrial engineering as a branch came into existence during the industrial revolution. Pretty obvious. So why? Because we wanted a smart way to manufacture things at large scale. So what do I mean by that? So let's say you need a particular, let's say you need to make a chair. You need 4 legs and 2 arms. Okay, you can't have 4 arms and 2 legs and say let's make a chair. You still have these 6 components. So you need to have those subcomponents at the right time and at the right place at the right time in the right quantity. Right? So so every product that you see around you, I think by now you would have known that there's so many interdependencies. So there are many different parallel processes going on which need to function in unison for producing, say, paper or a plastic film or anything. So industrial engineering teaches those principles of production planning, inventory management, logistics planning, or how do you use your resources in the most efficient manner to deliver the final end product. Okay, so it's also got applications in e-commerce today. The traveling salesman problem, you can look it up afterwards, and it's a very famous problem. Or you could talk to your friends in computer science. They deal with it in their algorithms classes. So traveling salesman problem is basically, let's say you have a sales force and he needs to go visit n number of places. What's the most optimal way in covering his route? Okay, this also sort of has a application in plant design in terms of structuring the different units. Okay, there are safety constraints and all that, but how to optimally space different units together in a large, say, steel plant or a refinery or something like that. And then you've got design of experiments, which is a more research focused course where you say, I have a hypothesis and I need to design experiments to test its various outcomes. So how do I do that? And the design of experiments teaches you a statistical way to come out with what are the different areas that you need to test. What are the parameters you can vary, and how could you effectively test your hypothesis? So what were my takeaways from this? This is all what industrial engineering has to offer, but what are my takeaways from this, right? So one was what happens in a plant impacts management profits. So if a plant manager decides to take a unit down for maintenance 3 months before a deadline, how is the whole inventory affected? How is the whole inventory line affected? How does that affects his commercials? That affects his sales. How is the entire supply? There's a domino effect. Okay, one engineer's decision has a domino effect which leads to probably even price rise or loss to the company. So that picture became clearer in industrial engineering. Second is something that I use in life: mathematical approach to decision making. Okay, so if you look up concepts in linear programming, non-linear programming, life is all problems that you get in life. When you look at it, it'll look like a big maze. It'll look like a puzzle. But take a step back and start looking at what is the objective that you want to get out of it. Okay, and what are the constraints? So any choice or any decision that you need to make in life, look at it from the perspective of what is the objective, what am I trying to maximize or what am I trying to minimize, and what are the constraints. Again, make the best use of and linear programming will tell you how to do it mathematically, but over a period of time you'll start developing your own algorithms to quickly derive solutions to those decision challenges. So that was a short overview of industrial engineering. I think next few slides would be on my first job, market research in petrochemicals, and a general big picture view of oil and gas industry. I think it's important to know what's happening. As students, we are sometimes disconnected from the industry, and I think it's important to know what's happening overall. So petrochem market research, right? So what's market research exactly? So it's basically trying to assess what your consumer wants. Okay, trying to understand your consumer better. So and it gets complicated in areas like ours, where all that the consumer wants is a plastic bag. He doesn't care if it is blue in color or green in color. But how exactly will you do market research for that? So that's a kind of a case study I will get into a little in a few minutes. So my first job was basically an amalgamation of both my degrees, so chemical engineering and industrial engineering, which we also call decision sciences or management sciences. So I started assisting chemical companies in decision making. So it was kind of fit together like a nice puzzle. And so I started in 2013 for a small company in Houston, which is probably the mecca of chemicals and oil and gas in the US. And and I worked there for about till 2017, so for about almost about 4 years. So yeah, market research, as I said, involves helping companies bring the right product at the right price to their customers. So this is a case study. We'll get into a case study of one problem that I worked on during my 4 years there. I instead of adopting a typical project approach, I'd like to take a more generic industry approach to why this is important. Okay, this is one of my favorite projects there. So food packaging, right? So food packaging, we don't realize how much things around us change very quickly, and this is one such example. So back when we were kids, like I don't know if you guys have seen this ketchup bottle also, but I guess this pickle bottle still comes up. So ketchup, pickles, cheese, milk, very ancient times it used to be packaged in glass. All these things used to come in glass. Cheese was actually packaged in waxes. We don't see that very often unless you go out and buy artisanal cheese. But most commonly, cheese comes packaged in plastic these days. Okay, so what was the issue with plastic then, right? Like this glass bottle was common even in mid 90s. So what was the issue with and you see this pickle bottle even today, right? So what is the issue with plastics? Like we even have we even use plastics for blood transfusion, but we can't package a pickle in plastic. Why? So reason being, a simple plastic film or plastic sheet does not preserve the freshness, especially in case of these acidic products, right? The acid leaches into the plastic, and it becomes stale pretty quickly. The shelf life is short, which is why traditionally we have these long shelf life products in our grandmother's kitchens in what we call chinaware or in porcelain containers. Okay, so so single layer plastic, traditional, commonly available plastic was not really suited for that. Now there were other materials like nylon, which could actually preserve the freshness, but what would happen is it won't bind with color. So you will get a very boring looking packet, which nobody will pick at the store. So we want something that both nylon can do and the plastic film can do, which is make this coloring thing, make it look attractive from the outside and preserve the food from inside. Okay, so and that was one challenge. Second, glass, although it solved that problem, it had many issues. One, transportation, right? So obviously glass is going to be heavier, take up more space, which means more fuel for transporting lesser units of the product. So then you're going to have breakage, and so these were two main issues there. Nowadays, what we have transitioned to is this we see all the time today, right? Like we see this ketchup bottle, Tetra Pak milk, and all of that. So we've got the new flexi pouches. How did this happen? We'll quickly see how that happened. But although the bottles still coexist, the fast moving SKUs, this typically open and use in 3 uses, or like quick single use sachets, all of them come in plastic. So there used to be times when restaurants used to only serve ketchup they used to store it in a bottle and they used to have it on your tables. You wouldn't get personalized ketchup sachets, right? Like you get with every pizza delivery today. So what really drove that? Now, because of that, the outcome of that was you got more variety in quantity. You got reduced transportation costs, reduced losses per unit. We get these attractive colors. It looks, branding is also taken care of. So something happened in the middle, that we went from things that look like this to something that looks like this. right? So what was that about? So the innovation there was called tie-layer resins. Okay, so this is a family of products actually. So if you look at this milk Tetra Pak, there are actually 7 layers of packaging material there. So the example shown here, there are 5-layer systems, there are 7-layer systems, and 9-layer systems also. Each one is used for a variety of applications. So depending on the end use, the simplest one that is shown here is a 5-layer system, right? So the first layer, outermost layer, is a moisture barrier. The second one is a tie layer. The third one is a oxygen barrier, again a tie layer and a moisture barrier. So now, why is this called a tie layer, right? Because the moisture barrier, the one that is in contact with the food, and the oxygen barrier do not stick to each other. So that's like polar substrates. Like this is when it starts getting technical. Okay, polar substrates like polyamides like nylon do not stick to non-polar substrates like polyethylene, different derivatives of polyethylene. So you need to have something in between that acts like a glue that puts these two together, and that makes it possible to have a packaging system like this. So if you look at a zoomed in view of these 5 different layers, it's a polyethylene layer and then a tie layer, a nylon or EVOH, and tie layer again, and then a polyethylene layer. So says usually in 7-layer systems, you have another additional, say, layer for finishing actually. So it could be paper coated in plastic, or a sheet for colors or something like that. So, and or it could also be different layers of different grades of plastics and all that. So but yeah, the most common or the most basic one is a 5-layer system. This is what goes into all your all pretty much entire food packaging that you see today is a multi-layer packaging system. Yeah, it makes it difficult to degrade, but on the other, so does it contribute to landfills and all that? Yeah, it does. But it also saves you fuel costs. It keeps your it makes food accessible to a lot more people. Somebody who can't afford to buy milk, for a 1 liter packet can buy probably a 200 ml Tetra Pak. So things like that, right? So it's got its own pros and cons, but this enabled a revolution of sorts in packaging. Now, what is this product actually? What goes into the chemistry of tie layers? And yeah, before I move on, there are other applications beyond food packaging. Example is automotive gas tanks. So gas tanks, as cars started becoming lighter because of fuel pollution standards, petrol tanks became plastic petrol tanks, and those also involve these tile resins. So squeeze tubes, that are another example, which is like your toothpaste tube, Move, Iodex, pain relief creams, all your cosmetics, makeup products, everything uses this. Okay, so this is something that is there all around us, but we wouldn't have thought about it until it came to something, looking at it from a technical point of view. So the technology angle of it. Yeah, what happens is the tile is also a polyolefin, has a polyolefin base, which is modified with malic anhydride to give it characteristics of good adhesion. So you take a polypropylene, you take high density polyethylene, LDPE, or LLDPE is linear low density polyethylene, is a variation of LDPE, and graft it with malic anhydride and make a sort of a glue out of it basically. So metallocene LLDP is it's a very common industry grade, which is made out of metallocene catalysts. If you recall, throwback to your chemistry classes, metallocene catalysts are one kind, Ziegler-Natta catalysts are one kind. So most of the common low-grade plastics are made out of Ziegler-Natta catalysts. Metallocene catalysts are used for slightly more demanding applications, and metallocene LLDP, because it serves demanding applications, also a little expensive, and that can also be used to make tile resins for, say, something like a microwavable food or frozen meat or something like that, or even gas tanks, I think. So anyway, so the choice of polymer base and the process of grafting it will depend on the end use requirement. Okay, So metallocene polymers, like I said, are more versatile. They're used in something like high-speed extrusion coating lines, where you need to have a certain melting point, so that extrusion coating lines are designed for a certain capacity. If the polymer should not, like, you should melt at the right temperature for the film, multi-layer film, to come out in the desired shape. So the sorry yeah. So traditionally, tile layer resins are modified with maleic anhydride. This was the first, probably. There are many variants, so you could use. There are many other compounds other than maleic anhydride which are also used. It's a two-step process. First step is you graft maleic anhydride into a polyolefin backbone, and then you blend the grafted polymer with polyolefins. So the diagram looks something like this. So you've got these resins, that would typically be like pellets that flow into an extruder, and you've got a maleic anhydride tank, and extrusion happens in the presence of a peroxide catalyst. Now, the important fact to note here is this should happen at a particular temperature. Otherwise, you'll have maleic anhydride forming homopolymers of itself. So that's not something that we want. And eventually, you form the tile layer compound, and it gets out to package. So this is the reaction for those who are interested. It's been 7 years, so I can't really explain what both the reaction chemistry behind this. I think I did this work in 2014, so my memory is a little weak. Excuse me for that. If you have any questions with the reaction, I think sir will be a better person to answer, or I'll look up and get back to you. Okay. So you need to manage the process so carefully that you don't end up homopolymerizing maleic anhydride. You end up with the desired tile layer resin, and finally, so because of the specializations, right? This is a product that's manufactured by a very few players. So now moving to the industry side of it. So why did I work on this project? So a client came to us, a European petrochemical firm, a Spanish petrochemical firm in specific. And they asked us if what is the market size of this product? Is this something that we could enter into? This is because, like, these specialized products, right, are typically so the each layer that I showed you are basically few nanometers in size. So there's a very little volume of the resin assets that goes into every film. But as you can imagine, the world of film packaging is so huge that everybody wants a piece of that cake. So this particular company was trying to figure out if they could be a part of this market, and if there's something is this is something they would be competitive in doing. So what we did was do the technology and application analysis, which I just showed you. Do an industry analysis, like analyze who are the suppliers, who are the resin suppliers, who are the maleic anhydride suppliers, who supply tile layer resins, who will be their direct competitors. And if you notice, all the resin suppliers are also tile layer resin suppliers. Reason being, polyethylene, polypropylene resins, pure grade, just the grades of LDPE and PP, PE and PP are not really high margin products. Okay, they are high volume, low margin. But something like tile layer is what we call specialty chemicals. It's manufactured in smaller batches. It's a batch process, smaller batches, and technology know-how is not very commonly available, and small volume size is small. So these are small volume, high margin products. Okay, so you just cannot make a multi-layer film without tile layer resin, and that. So imagine the power these companies have in the entire packaging value chain. Okay, so this is so the industry is concentrated in the hands of a few large companies in each territory, like North America, Europe, Asia. Mitsui is a Japanese company, Dow, DuPont in the US, LyondellBasell, both US and Europe, more so in Europe. Arkema is more Europe. So and then it goes to distributors who are like today, even Alibaba, IndiaMart, they qualify as distributors. And finally, end users are converters who are producing these films without getting too much into the technology side of it. So they'll get a resin, PE resin, they'll get nylon, they'll get tile layers. They have a huge extrusion coating machine. They'll put them all in, and they'll produce the final colorful looking packet for Kisan. So this is how the industry works. and we had to do an estimate of market size. Now, this is a very difficult exercise because it's a very special product, right? If you go and look up what's the sales of tile resins, you're not going to find a lot. So you're not even going to find tile resins results a lot. So how do you estimate that? So you estimate it based on how much resin is produced, and assess, so and that you could assess based on the production unit sizes. And so that's a top down approach, which is coming from how much production happens in the world, and a bottom up approach, how much resin is consumed in each application. So you've got like film packaging, automotive gas tanks, then some pharmaceutical products. So in each product, like what, how do you, you take an estimate of what's the amount of resin that could be used, and make a bottom up estimate. Okay, so and then make a top down estimate based on who producers are very few. So what is the approximate unit size? What's the batch size they produce? You can get that information by talking to people mostly, and if industry veterans would know that kind of information. So make an assessment based on that, and you need to tie up the two. So there's a little bit of mathematical craft involved in it. Okay, so that's kind of the work I did for this Spanish petrochemical player. Right. So, and based on this, they'll take an internal decision as to if this market is attractive for them to make an investment, and if they could buy a unit that produces tile resins. So this kind of feeds their decision making process. Now, stepping back, if you have any questions about the previous case study, keep that, make a note of it. We'll get back to it later. So now stepping back to take a look at what's going on in the oil world, right? So there are three questions that I plan to take up. First one, why is oil still relevant in a world that recognizes climate change? Second, what has happened in the oil industry over the past decade? Third, my assessment based on the little experience I have in this industry of where these oil majors are heading towards. So first one, this is sort of a question that I want to throw open to the audience. We know that all the plastic in this world comes from crude oil. So what percentage of crude oil gets converted into plastic? Is there a guess that I could get from the audience?
Yeah, they have to, I think, unmute and tell, or you have to. Yeah,
Oh, okay.
probably. No, I'm telling to the students.
Okay.
So you can just unmute and tell your percentage.
10%.
Okay, 10% is one. Any other guesses?
One has texted 1 to 5%.
Okay.
One has texted 30 to 40%.
Okay. So,
Okay,
so that's quite a wide range, right? We've got anything from 1% to 40%. So okay, so let's see what happens.
4 to 6%.
Somebody Googled it, so that's the first result you get on Google. So that's right. Actually, it's about 5%. In some cases, it's less than 5%. Like countries that export, like India, that exports a lot of refining product rather than produce special, end-use plastics. It's less than 5%. But in the US, it's about 4 to 6%. Okay. So this is something that all of us would know. 1 barrel of oil, what all it could produce, like fuel, mostly it's fuel. Majority of oil goes into making some sort of fuel. Then a little bit of power in some countries. Again, this is being phased out. This is not all that common in application. Then you've got these liquefied gases, LPG, and all of that. Lubricants, waxes, asphalt for roads, road tar, and all that. So then after that comes about 5% or less than 5% of the fraction that's comes out of naphtha as a starting product and goes into everything that you see around you, basically. Okay. So why is oil still relevant? Because of this. We can't get rid of all of its end use overnight or even over a decade, or probably, let's see, even for probably over 2-3 decades together. So whatever be it, even Tesla runs on plastic. Okay, Tesla has also got plastic components in it. So there is nothing that's purely green. We are all moving towards a world from black oil to somewhere in the gray. Okay, green plus black. So anyway, so why this story? So a little bit of industry insight. I think this is also pretty commonly known stuff. So you've got oil industry is typically divided into upstream, midstream, downstream. You've got exploration and oil field services in the upstream. Midstream is all about pipelines, processing, getting it from the offshore rig to onshore and then getting it to the refinery. And finally, refining downstream plants, retail distribution, sales, and these are companies that are engaged in these businesses. Plastics starts from crude oil, natural gas refining, and the refined naphtha goes as a feedstock, and then it's converted into end products. So Sealed Air is actually an interesting company. There are some case studies around Sealed Air if you look at it. They're basically selling air in a plastic bag, and they're making tons of money out of that. So it's a great company to work for actually. If they're selling air. Then so this is what's happened in the past decade in the whole oil industry, right? So last decade of oil has probably seen so many fluctuations that have not been witnessed since like World War days, I guess. So it's been an interesting decade. See, oil prices went to negative. So let's quickly look at what's been happening. First, in 2012-13, right about when I started working, was the big boom because of Arab Spring. So Arab Spring is a political crisis that happened in Libya, Tunisia, Syria, Egypt. So all these countries are oil producers. Their production got affected because of that internal political crisis, and we went into a period of low supply, high demand. Therefore, price increased, and at $100 a barrel, shale gas gained a lot of prominence. Okay, so shale extraction is basically extraction of oil or gas stuck in between shale rocks through a process called fracking. It's a far simpler process than on surface. It looks like a far simpler process than drilling, offshore drilling. But there are a lot of environmental concerns associated with it. But it gained prominence because it became, for the first time, the shale fracking technology has existed for 30, 40 years nearly. But for the first time, it became profitable to extract oil and gas from shale rocks. Right. So a lot of investments happened in the US. One of the more interesting aspects of it is oil or gas that's extracted from shale deposits has a different composition compared to oil that comes from offshore rigs or any crude oil deposit, right? So what happens in the shale gas deposits have a fewer are rich in lighter hydrocarbons and not so rich in the heavier ones. So you don't find a lot of propane and butane derivatives as much as you would find in the traditional crude oil. So what started happening in Houston or US Gulf Coast, as we call it, was a lot of people started investing in on-purpose propane and on-purpose butane plants. What do I mean by on-purpose? So these plants would be solely dedicated to producing propane. Reason being, polypropylene and derivative of propane, polymer of propane, has extensive applications in everything from automotive to pharma. Okay. Similarly, butane is what entire synthetic rubber industry, starting from tires to engineering plastics, anything that's synthetic rubber uses butane derivatives. So without these two, world would not be functioning as we know it. So they started making these investments because they thought oil is going to be this high. People didn't recognize that Arab Spring would turn around, or there'd be other regions that's producing oil. So they always, when you're riding on an optimistic wave, right, you tend to get over optimistic. That's what happened at that point of time. And then in 2015, 16, 15 is right about when everybody started feeling some issues in crude oil supply chain. 16 is when probably it hit the worst. So there was a huge supply glut. Production in Middle East and African countries, OPEC countries started increasing. Price fell down from $105 to $29, $30 a barrel. Okay, so shale oil investments were no longer viable. Now all those guys who had invested in shale oil field services or invested in plants because they thought shale oil would gain prominence went bankrupt. So many people went bankrupt during this period. It was a very difficult time for the industry as such. There was a lot of so when such things happen, right, there's a lot of activity among investors. So all these private equity investing firms start buying these sick assets out. They'll turn them into something. They'll turn them for a little change. They'll keep flipping them for a small profit. So they'll start doing something else out of it, or they'll find a buyer for it. So a lot of financial engineering starts happening when such deep crashes happen. Anyway, so now next, the recent one, oil went to $15 a barrel, and for a few sessions or less than a day, probably, I'm not sure about the time frame, it actually went to negative, meaning there was so much inventory, then there was so much supply that people didn't have the space to store any oil, and demand crashed because of COVID. So now, as COVID concerns in other countries are easing, demand is coming back up a little bit. Optimism is returning. I think last price that I have on hand is around $63. So if you look at natural gas, right, it will also follow a similar trend, but the numbers will be very different. The trend won't be very different. Numbers, the whole absolute numbers will be different. But yeah, this is what's happened so far. So we've gone from a period of extreme optimism that oil is everything. We North America and Europe were riding on a huge high cost because of political issues in the Middle East. To supply glut, OPEC couldn't listen to North America. OPEC couldn't listen to Europe. They started producing more. Venezuela went into a deep crisis at this point of time around 2016. So point being, although oil has an impact, there's a reason why oil still causes wars. Okay, so a small political issue somewhere in the world can change job prospects for chemical engineers. This is hitting hard back home, right? So many chemical engineers in the US lost jobs because their oil fields were closed. There was a huge project that Shell was going to get into in extracting oil in Canada, in the Arctic. All of that was shut down. It's still shut down. So many exploration projects basically got scrapped, and it still remains scrapped. It still hasn't recovered fully. Although it looks 63 and 105, things are looking up. There is so much of existing inventory overhang from all these years that we still need to burn. And India is a large consumer, and India in its second COVID wave, things are still not looking very up. We don't know where this will go next. Now, where are oil majors heading towards? Now, see, if Shell or ExxonMobil are such huge, Shell, ExxonMobil, Chevron, BP, all these large oil companies are sitting on such huge cash deposits. They've been in the business for decades together, half a century, more than a century is sometimes, in fact. So they realize that they can't survive in a world where price goes from 105 to negative in, say, 8 years, right? So they need to do something about their business. And also there's pressure around these companies being the so-called big dirty oil companies. Now oil is ubiquitous. You can't stop refining. For all said and done, we need oil products for a little more for so many years more that I know into the future. But the growth is going to shift towards renewable energy solutions. So if oil grows at say 0.5% demand every year, our renewable energy will grow at say 6-7%. Like the numbers are not accurate, but it's just a estimate to show you kind of the pace at which things will grow. So shift is companies are seeing a shift towards renewable energy solutions. Statoil, which is probably Norway's one of the oldest oil companies in Norway, rebranded into Uninor. That happened a few years back. So they call themselves Uninor. They call themselves an energy company, no longer an oil company. They removed oil from their name, basically. Shell is going on an acquisition spree. They've acquired power utility companies in UK. This is a utility company, I think, in Germany that they've acquired. So they are rapidly becoming a power and overall energy services company. Okay, so all kinds of energy you need, be it for your car or be it for your house. Your car could run on electricity or your car could run on petrol. Shell is there to service your needs. Another favorite one is electric vehicle charging stations. Oil companies are used to supplying fuels for cars. If you snatch the biggest business away from them, they're going to find this is their next best alternative. They want to find ways to come back as EV charging networks. So a lot of interesting work is happening there because startups in this area, right? They've got the tech expertise. They don't have the money that big oil can provide for scaling up. So I think this is a very interesting trend that's happening recently, that big oil companies are moving towards green energy startups. So now, as students or as people who are looking forward to getting a job in this industry, what is important is you need to be versatile. So a refining engineer cannot expect to be a refinery engineer cannot expect to be a refinery engineer and throughout his life. The refinery might be shut down or he might have to learn new skills. So versatility is the key to survive in this changing business environment. So this is a good segue into why MBA. Okay, so why MBA? Takeaways from MBA, overview of consulting and renewable energy, and finally I'll close the session. So this is a clip I want to play. Most of you would have seen this. Can you hear the audio?
No, we can't.
No, unfortunately, this in Google Meet, I think audio
Okay.
will not get connected.
Oh, okay, fine. No worries. So this is a scene from a Vijay movie, okay, Nanban, and that remake of Three Idiots, basically. So he says, bank la vela paakradhukku edukku engineering pananum. Okay, so that is a very common misconception. Something that I'd like to clear off here, that engineering and MBA have nothing in common. You've wasted. So there's so many people who've told me that if you shift to an MBA after engineering, you wasted an engineering seat. You've killed an engineer. Okay, so there's nothing so dramatic about it. Engineering and MBA have a lot in common, and in fact, good engineers make up for really good, make help the industry move along. Okay, so the example for that is so what were my takeaways from MBA, right? First, I'll do that, and then I'll show you an example of how engineering and marketing and sales and all these things come together for making a better product overall. So MBA helps build versatility. It helps you to quickly adapt to changing industry requirements, like I said before. MBA helps in recognizing the big picture. It teaches you how to think about the industry at large, and it ties together all skill sets towards solving a problem. So throwback to your in equipment design class, where you take concepts from thermodynamics, take concepts from heat transfer, mass transfer, reaction engineering to design an equipment and make that drawing for for the class, right? So just like that, it brings together economics. MBA brings together economics. MBA brings together psychology. MBA brings together a little bit of engineering, statistics, all together to just meet consumer needs, right? So in any production, so this comic is Dilbert is a very excellent, very realistic comic for showing you what really happens in the outside world, right? So salespeople will blame marketing, marketing people will blame engineering, engineering will again blame customers, saying, oh, the customer didn't know what he wanted, that's why the product was a failure. So this goes on all the time, again showing that we don't work in isolation, we work together as a single entity. Now, this is a case of shampoo bottles. So if you recall, there used to be a disc type shampoo bottle cap, right? So where you hit press on it and it pops up open. And nowadays we only see the flip type, where you flip it up open, right? So there a lot of market research went into this shift from disc type to flip type caps. This is a reason being flip type uses real recycled materials, and uses lesser plastic actually. So the marketing team at Procter and Gamble, I think Procter and Gamble, if I recall the company right, went out to conducted a large scale survey to see if consumers actually had any value in disc type, in opening a shampoo bottle this way or in opening a shampoo bottle, flipping it open. So yeah, so now so these are different parts of a shampoo bottle that were re-engineered simply based on market research. So the cap became flip type with because consumers said they really don't care how it opens as long as shampoo flows out. Then labeling started getting different to reduce costs. cheaper plastic, cheaper printing material, recycle, use more recycle. This is also again very interesting. The bottoms, right, used to be the older Johnson & Johnson ads. If you look up, the bottoms will be rounded bottoms. So when you package it, it will look like, the last figure that you see here, last part of the figure. Packaging will not be efficient. There's a lot of gap. But if you pack it as squares, you will see a lot more space, a lot less space wasted, and a lot many bottles packed in the same container. So this is kind of how FMCG companies started using more recycled plastic, changed their product design to adapt to recycled plastic properties, or to adapt to cheaper costs, better packaging, and all of that. So this is an example of how engineering came together with marketing, market research, came together with logistics and distribution, and they engage with the consumer for ultimately for making a better product, which solves the consumer needs without making the environment significantly worse. Today, a lot of FMCG companies use recycled plastics. There's a whole world out there of startups that are engaging in plastics recycling. There are its own set of issues. That's a separate another 1 hour session to get into. But for now, I'd say if anyone is looking to start up, waste management is a very good area. So problem statement. So moving on to renewable energy, I think this is the last few slides. I think I'll be done with this in a few minutes. Problem statements that I work on as a strategy consultant in renewable energy, right? So as I was saying, oil majors started buying renewable energy companies. I moved from oil to renewable energy. It didn't happen by plan. It was just by chance. Okay, so it looks like a very connected fairy tale, but that is in hindsight. So in India, you see GAIL also following the same aspect. So I worked on a project for them on setting up EV charging stations, electric vehicle charging stations in Delhi. There's a startup that does electric vehicle cab aggregation services. So an Uber only with electric vehicles. And then, so what I did for them was business model. How do you charge consumers? What is the best market entry strategy? How could GAIL use its strengths in gas distribution to leverage that for electric vehicle charging, all of that. Then policy papers. This is something that we do in KPMG a lot. So we wrote policy papers on. This is a public source. It's available. You could just look this up. You can download it, and it's a fairly longish document, but it's got very interesting solutions to on renewable energy. How could you use innovative technology solutions for increasing renewable energy use? So one of them, which is actually gaining a lot of interest these days, is hydrogen. So hydrogen, as we all know, has a myriad of end uses. There's so many end use applications for hydrogen, and one of the one of these applications that is studied right now is using solar energy for electrolysis of water, getting hydrogen out of it, using that hydrogen to in a fertilizer plant, or say make fuel cell, power a fuel cell and run a bus out of it. So Tata and Indian Oil actually, this is again available in public. Tata and Indian Oil actually have worked on making a fuel cell operated bus. And there is a fuel cell refueling. Hydrogen, of course, has constraints with refueling and storage and all that. So Indian Oil operates a refueling center hydrogen refueling center in their research facility, I think somewhere in Delhi NCR, in Ghaziabad, if I'm not wrong. So these are really interesting things that might see the light of the day in the next 10 years, 15 years time frame, or probably even sooner if the government wants to put funds and act on it, because most of these are PSUs in India. So then another one is solar power for agriculture. This is a very big, very hot happening area right now, because a lot of states, including Tamil Nadu, provide agriculture power to agriculture consumers for free. What it does is, so farmers get power to their pump sets for free, right? So, and because it's free, they don't get it in a regular schedule. They get it as and when the power department feels like. So if you always ask a farmer, he'll say, "Oh, I got 2 hours of power at 4 a.m. I got 3 hours of power at night 10 p.m. Somewhere in between, I got 1 hour of power." And because the mandate for the utility like Tangetco is to provide 7, 8, 9 hours of power or something like that. And or if all things work fine and if they get full day of power, they end up extracting more water. So groundwater levels are at an alarming level. I'm sure all of you would have seen a picture from NASA which says, which has like red all through India's map saying these are extremely scarce groundwater areas. There is absolutely no water left. And I actually visited a place in Rajasthan where these guys said, we have to switch on the pump, wait for 15 minutes. There'll be some water that comes out. Again, there'll be no water. Switch it off. Switch on the pump again. So they keep doing this on a 15-20 minute interval. That's how bad the groundwater scenario is. So we call this the energy food water nexus. Okay. So we need more food. So we use more electricity to pump water. So and groundwater resources get depleted. So this goes on as a circle. And if you provide free power, all the more better, right? So free power, more water, more food. So this is like going in a endless loop, and there is so much work going on. Even the government is taking a lot of initiatives to break this. One popular initiative is what we call the Kusum scheme, PM Kusum scheme. What the government is trying to do is set up a solar panel next to the pump set, where the farmer could actually use power from the solar panel, and when during the hours when he is not using the pump, he will sell power back to the grid, so he earns a revenue. And that is to encourage the farmer to use less water, and at the same time we are not providing expensive power from coal for free agriculture uses. So finally, an outlook for the energy sector, overall energy sector. We are seeing an increasing electrification of end-use sectors like transport. Fuel cell electric vehicles will coexist with lithium-ion battery vehicles. Power generation is moving from centralized to distributed. This is a very, very big bang change that's happening. So earlier we used to have like there is one coal power plant in Neyveli which is supplying to so many places in the state, in other states, in the entire south zone. But now we are moving to having solar rooftops in every building. Okay, so how will an entire supply system that was designed with one production center and many consumption centers move to many consumption centers? I mean, many production centers and many consumption centers. That is the distributed pattern. So this is a very big challenge that the industry is facing, and there are many solutions, and each state is in its own ways trying to solve this problem in India. So now solar has become cheaper than coal. Solar power is now at 2 rupees per unit. Coal is at around 4 to 5 rupees a unit in most places. It will be higher in places which are far away from coal mines and lesser in places that are closer to coal mines. So solar generation increase is going to happen, which means we need storage systems. So all those into research, please look at electrochemistry very seriously. It's going to be hot for a long time to come. Material sciences, electrochemistry, anything to do with storage is going to be very, very interesting. Green hydrogen, something that I mentioned a little while earlier. Then future sources of power, we're going to have offshore wind a lot. This is another thing where offshore oil extraction is helping us. So all these companies that know how to set up an offshore rig are transitioning into setting up offshore wind plants, because wind speeds in the ocean is more consistent. The issue with solar and wind is that it's not as consistent as a coal plant, right? So you burn coal, you produce steam moves a turbine, you get electricity. This happens like clockwork. There is no variation in this throughout the day. But solar and wind, you get 10 minutes of cloud cover, power is gone. You're not going to get supply for another while. And night, no solar, no supply. Wind is again very seasonal. Monsoon seasons, it's crazy, and off monsoon seasons, it's summer and other seasons, non-monsoon seasons, it doesn't produce as much. So we need storage. Offshore wind is getting really a lot of traction because we've got a long coastline which we can use, and although it's a little expensive, it's still more reliable. So I think in a few years, offshore wind will also become cost competitive. So that's about the takeaways for the energy sector. Now, closing all this, right? So how does all this tie together? what are the takeaways, what is the bottom line, what are the takeaways that I want to give you guys. So first one, always ask why. So understand what is the purpose of anything you learn. Okay, so why is it that this plant is designed in a certain way? Why is this unit placed next to this unit? Why do you have, so these whys will make you a better engineer, and in turn more sound, I mean a technically sound person basically at the end of the day. Whatever you do, ask why. Second, connect the dots. So this is what I think gave me a very serious competitive advantage in the industry. Right? So because I know where hydrogen is used, because I know how solar energy needs a storage system, I can link that to say how a market for green hydrogen can be created. So connecting these dots from what you learn. So for you, from a classroom perspective, connect the dots from what is happening inside the classroom and what's happening outside the classroom. So read newspapers without fail. Understand business news for sure. Okay, if you're somebody who's interested in not, I mean, who is not interested in research, who wants to get into the industry, please understand. Please read. Make the habit of reading the business column every day. Okay, and try to figure out why is this happening, what is happening, and connect it to what you learn in class. There is a connection. It's not obvious, but there is a connection. Finally, find your purpose. Okay, this is a very difficult one to do, but keep thinking about what makes you, what fascinates you. You know, what is that question that intrigues you the most? What is it that you want to be? Okay, keep looking for that within yourself. Last one, find your, again, as part of find your purpose, also find what makes you happy, because you can't get up every day and go to some place that is boring. Okay, so find what makes you happy, like this Calvin and Hobbes comic. There's so much that's available under the sun. If you found really what makes you happy, you will be the most contented individual in this world. This also applies to kind of why I came back to India, right? So working here, you know, sort of, you know, I get the feeling of giving back to my home country and all that. It gives me a sense of purpose. You know, there are a lot of other issues, but still, it makes me happy. It gives me a sense of purpose. It helps me sleep peacefully at night. So that's it from me. Before I close, I think I have a few pictures from what used to be the chemical engineering department 10 years back. I'm not sure if Chandru sir and
Yeah, very nice to see Chandru. The other is Sivakumar, right?
Shivakumar sir. Yes, Shivakumar
Oh,
sir.
he's very young. Yeah, they are there. Both of them are there.
Yeah. So Shivakumar sir is an amazing guy. We won the equipment design competition because of him. Okay, so he made us a really cool cooling tower, which won us the contest. So yeah, so this used to be the chemical engineering department, and we ourselves moved out of it in our third year to Jana Chaitanya. And yeah, this is no longer the chemical engineering department, and this used to be our mass transfer lab. This I think was heat transfer lab. Yeah, I'm not sure. Yeah, so yeah, that's about it. So any questions? Please
Yeah,
go ahead.
yeah. So there is one question that is already texted. I think you should take a water. It was very energetic talk. Huh? So you gave a complete perspective of what could be a chemical engineer. A chemical engineer can do probably many things, connecting the dots, finding the purpose. So that's something very nice. So you want me to read, or you'll go through the chat? So it is in the Google
Yeah.
chat.
Chat. Okay,
So
1 minute.
yeah, you can start with the question of Harish, and in the meantime, I would ask others to put your question in the chat so that she can take it up.
Yeah.
So this
So,
question of Harish.
MLPs also have a 70% cardboard base, so when they're fused with polyresin, they recycle. They often end up being single use. Even chemical recycling processes have been unsuccessful. Any idea if there have been attempts to the packaging markets to address this? Okay, so Harish, the answer is in short, there must be some attempt, okay, on how to recycle this, but the fact remains that it's very difficult to recycle multi-layer packaging materials. Okay, it is single use. It is difficult to recycle, and everything that's got a con also has a pro. Like I was mentioning, multi-layer packaging has enabled access to different products, like your 1 rupee shampoo sachets or your 1 rupee ketchup sachets. that were not accessible to many people, and it's important to have products at that price point. Okay, so it's enabled improvements in quality of life for a lot of people, but yes, it's not environmentally sustainable, which is why you start seeing so today you have a lot of startups selling A2 milk in glass bottles. Okay, that used to happen in the UK in 60s or 70s. If you see old Netflix shows, it will show you Netflix shows set in the 60s 70s, it will show you glass bottle milks. Like, it doesn't happen anymore because of a reason. So yeah, so recycling is a concern. There must be some attempt which is still in the nascent stage to address this, but it still remains. So do these firms even think of post consumer issues of their products? This is something they've started to think about. It is not that the post consumer issues is not what moves their share price, which is what the CEOs are concerned about at the end of the day. So they've started to think about these as a potential risk or a potential issue that might come back to bite them at some day, and it has. Okay, there are very interesting cases of look up DuPont Teflon Virginia. I think it was Virginia or Connecticut. Look up DuPont or Teflon's case in Virginia or Connecticut. It's a big story. There is I don't want to go through it right now. A lot of you must be hungry already. So they don't give it as much importance as we want them to, but it's changing. It's in transition right now. So yeah, and then what made you pursue second masters, and do these companies intake people from multiple specialized or narrow field or specialized ones? So there is really nothing. So my objective of the talk was, again, I'll reiterate, there's really nothing called a narrow area or a broad area. Okay, there are. It's what you make it out to be. It's how you see it to be. So I can't you know do write 1,000 lines of code and do the job I do, and the guy who writes 1,000 lines of code can't do the job I do. So there's a place for everyone in this world. So there is, so because there's a place for everyone in this world, there's a company somewhere who wants to hire you, or you could make your own startup in this field. So literally sky is your limit. There's so much to do under the sun. So reason for my second masters was because oil industry sort of started flattening out. There is only so many companies in chemicals that had market research questions, and my project started getting very, very repetitive. So on a daily basis, I used to have like 5 hours of work, which was mostly recycling an old calculation that I had done for another client for a new client. So it got very boring, and I didn't want to be stuck in a boring job at 25, 26. I thought I still had the time to experiment. So, which is why I wanted to be more versatile. And a lot of these jobs, the next level jobs, involved some financial understanding, which I didn't have at that point. So I thought an MBA would give me that finance, economics background as well, which is why I came back to MBA. Then, and Srinivasan, hi. I just wanted want to hear from you. What would you do when you're stuck at some point in your project or work? How to streamline the mind to trace back and look at some ways of solution. So this I throw back to that point where I said, look at the objective. Okay, there are every day we get stuck at doing something. In fact, most common of issues, right? Like I'd be working on a presentation and I'd get stuck or lost in the formatting formalities. So simple things like that. Just step back and look at what you are trying to do. Most often, what happens right now is if you get stuck at a problem, you keep it aside, scroll through Instagram for 15 minutes, forget about the problem, come back, the problem still remains. Okay, and by now you've forgotten about it, so you have 15 more minutes to spend for understanding what that problem was, and then you end up wasting 1 hour. You don't realize how things go. So you feel hungry, you start eating. So the whole cycle repeats. It goes on in an endless loop of unproductivity. Instead, step back, write down your objective. So what am I trying to do in this exercise? And come down to what are the different steps that you need to do. And when you so what works for me is I write down things in bullet points, and I say, okay, this is my objective, this is where I need to go, and these are the 5 different steps, and where am I stuck exactly? And then I try and figure out, why am I stuck? So then there are branches, or there could be different root causes of that. Then you analyze it. So try to put it in a picture format, or try to think out in your mother tongue. A lot of time talking to myself in Tamil helps. So a lot of that. So then I hope that answers your question, Srinivasan, because this is something that everybody every day is trying to figure out. So Gokulnath, I'm an operational oriented person from pharmaceutical industry. If I have an idea to pursue management degree, what sort of mindset or career aspect I could look upon, and how would it help me step up in a career? So pharma, I think, is obviously, we all know, we want vaccines, we want more vaccines, we want it faster. So yeah, if you're an operations oriented person, there's so and in pharma, right? So pharma, the king in pharma is the researcher, but unfortunately, I mean, all the operations ops guys are also equally important. There are quite a few interesting startups that are working in this area in the field of uh, getting lab tests home, or getting doctors home, or getting medicines homes and all that. So it's a very broad question. I'm not really sure what exactly you're looking at. Career, in terms of career, there's pretty much everything you can look at, from e-com to, again, go back to pharma and do portfolio management, or again go back to pharma and say process improvement in pharmaceutical manufacturing facility. So there's literally everything. So can you throw some light on LNG and its future, considering huge investments planned in that area? So LNG, natural gas is still the workhorse in terms of power production in US. Okay, Europe is transitioning out of it. US is still heavily using natural gas for power plants. LNG in India, there are not many reserves. We already burnt our finger with Krishna Godavari Basin. But LNG is a much more cleaner source. Like, obviously, it's a cleaner source compared to crude oil. So for all you know, the crude oil extraction could reduce, LNG could increase to produce the same amount of end products. But yeah, so which is kind of the reason, because of its relatively clean image, is why LNG is getting a lot of investments. But I'm not sure about how far these investments would go in India. But outside of India, US is a huge LNG market. So that is one. Then Vignesh, do you think all nations could practically reach the goals set in the Paris Climate Summit? Okay, this is political, economic. This is like a very loaded question, especially India. So India, I think, there are a lot of representational issues. Like, if you look at older reports, they'd say hydro is not really renewable energy. Large hydro projects, they'll say mini hydro projects which are less than 25 megawatt, or 10 15 megawatt, 10 25 megawatt, I think, is the cutoff. Mini hydro projects are considered renewable. Large hydro is not considered renewable, simply because of the environmental damage large hydro causes. Now, countries that want to meet this target, right, they start branding it as non-fossil fuel sources of energy, and we have so many gigawatts of non-fossil fuel sources of energy. So India is actually doing a very good job in terms of meeting its targets. We might not meet it in the exact quantity, like we set out like so many gigawatts of solar, so much of wind and all that. The portfolio might vary a little bit, but we are taking the right steps. We are taking the right direction. Will we get there? We hope to get there. That's how the policymakers are working towards that. I can tell that for sure. Like, having interacted with folks from MNRE in Ministry of New and Renewable Energy Resources, they're working towards that. But the objective is to do that without increasing costs for you. You don't want to pay a higher power bill. Okay, so they're doing that fixing operational issues in power sector, increasing renewable energy integration, so that they could get to the Paris Climate Summit. I can't comment on all nations. India, probably it can, if it goes in the same pace and accelerates a little bit right now. So I think that's it, right? There are no more questions.
Let's wait for a minute or two.
Yeah.
So maybe students, if anybody wants to unmute and ask, also you can unmute and ask. So any first year wants to ask, you can unmute again and ask. I think your classmate has come, Anusha. I could see her.
Oh,
So probably Sadhvi is there.
hey, hi, Sadhvi.
Yes. Right. So yeah.
Hey,
So
Anush.
what?
Hey, Anusha. This is Rohit. That
Hey,
was a
Rohit.
really
Hi,
nice
hi.
talk.
Yeah, thank
Okay.
Hi,
you.
Naren sir. I'm also from 2011 batch.
Oh, good. Very nice. That's good.
Yeah, this is a very good speaker series that you guys started. It gives very good insight into industry to really like. This is
No,
the thing that's missing. It's not exactly missing. People, if they're interested, like Anusha, they always know what they want. But people like when they're in the first year and second year, this helps them understand like, okay, what do they want to do? At least when I joined chemical engineering, it's not like I know why I want to get into chemical engineering. Quite frankly, that's the only one of the few branches left when I got into admissions panel. So if it was something else like mechanical or civil, I would have taken mechanical probably. So it's okay. I get it. It's okay for not getting a good clear view before you join, but these speaker series will help you understand what you want to go, where you want to go from here. Very good initiative.
so you should tell how was hearing to your classmate after a decade in a very different forum.
Exactly, that's impressive.
I mean, how was it hearing to your classmate?
Rohit has heard enough of us in the class itself. So we used to be quite a noisy group.
So that means then I'll take this as a very good chance to rope in now. Then probably next Rohit should talk for the next month or something. So I will catch hold of you.
Yep,
Nice,
yep.
nice.
I
Thanks,
would love
Rohit. Yeah,
to join. Yeah.
yeah, good. Anybody else who wants to unmute and speak? You are welcome.
Hello, sir. It's me, Srikar.
Yeah, Shrikar, go ahead. Go ahead.
Hello.
Yeah, go ahead.
Hi, Ka. So I have a couple of questions. Is there any role of data science and machine learning in what you do in your daily life? You said you won't be writing the codes, thousands of lines of codes. That is true. But is there any way which uh, adding that to your CV will help you?
Yeah,
I
yeah,
just have a
massively. Okay, so so data sciences in research is an entirely different suite of applications. Data science is in a techno-commercial role. I'll give you the example of renewable energy, right? So we've got this is a very this is a problem where a lot of companies are trying to make products. So we do not know when we can't predict the weather, okay, but we've got so many satellites up there that are trying to give us a forecast of what tomorrow will look like. So we'd like to know at a given location, if I put up a solar plant there, what is the exact amount of power generation that I'll get on a hourly 10 half hourly, 15-minute, 5-minute intervals. Okay, so the main thing about power systems which is different from oil and gas or anything we are used to as chemical engineers is supply should equal demand at all points of time. So we do not have store a lot of storage as yet. So right now today we are setting up a lot of solar plants, and we need to know the connection between cloud cover, weather forecasts, and power generation. And this is a big data problem because you've got to analyze years and years of weather data at that particular location, along with solar irradiation at that particular location, and then the what kind of the wafer is the solar panel using. So there's so many variables there, and this is a big data problem. And another one is how would demand vary, right? Even on the AC, because supply should equal demand. If you are forecasting or if you are doing some sort of a machine learning exercise on the supply side, the machine learning part will kick in, where you have enough data to train the model on solar generation impact of generation on, weather impact of solar generation. If you've got enough data to train the model on, you could just get more accurate forecasts. And there's something called a load dispatch center where actually engineers sit and plan what should the next day schedule look like. So how many coal plants should they dispatch? How much power should this coal plant produce? How much power is expected to come from solar? How much will come from wind or hydro or any other source, right? So this would help solve a lot of problems. It would make renewable energy more competitive, in fact. So this is one application. On the demand side, let's say there is predicting demand changes again with weather or again with other variables. Like there was a COVID. So classic example is this Earth Day, right? Every year there is a Earth Day, and people switch off their lights for a few minutes. So that's a huge sudden drop in demand that grid operators have to balance. Earth Day is predictable. COVID-related shutdowns was not predictable. Then there are some other issues, technical issues in the plant that could trigger such demand, supply side issues or demand side issues for that matter. So in short, yes, there are like, even in power systems, even in renewable energy, there are so many applications for data sciences. Having a data sciences background will definitely help.
Oh, okay. Thank you. Like a attached question I had, which you kind of answered, regarding the power dispatch system. Before even the plant is set up or the power dispatch system is set up, so you mentioned in your talk that the energy is going completely distributed, and there'll be energy coming from various sources. So this is a problem of energy integration. And how do you think chemical engineers, especially who are graduating now, can upskill themselves to contribute to this issue?
So, see, you could look at it from an entirely technical standpoint and start looking at what is the, how do I how do I look at voltage in a particular distribution circle, and how do I integrate so many units of solar generation coming from, say, one village with the larger grid. You can look at the technical angles of it. That will be stepping into an electrical engineer shoes. But how can chemical engineers upskill themselves to this distributed power generation? It will be sort of an integration between electrical and chemical. One principle is storage. So find a cheap, low cost storage solution that you could just fit behind a solar panel. Lead acid batteries are environmentally bad, and they don't they don't work as long as lithium ion batteries. Lithium ion batteries are too expensive. So find a material, find a storage system. So as a chemical engineer, if you want an exciting problem, find a storage system that could store power from. It needs to be flexible, so the reaction needs to be so fast that for 5 minutes, if the grid is not accepting power, the storage system should quickly accept. And if similarly there's a drop in generation, the battery should back up with backup for power supply. So the reaction inside the storage should be so fast that it quickly adapts to these changes. At the same time, it should be safe. It should withstand heat, temperature, all these outdoor conditions, and it should be cheap. Okay, so that's a chemical engineering problem for you to solve.
Okay, thanks, Siva.
Yes. So anyone else wants to just sum up or give a greeting to Anusha? You're welcome. So we all these not only current students, Anusha, we also had graduated students. Like for Shrikar is graduated from last year. Gokul is a graduated student. The one who asked question, Harish, is also a graduated alumni. So you have students right from 13, 14 onwards in this meet. So that's very nice.
Yeah.
Right. Yeah. So if there are no other questions, let me join hands, and thanks a lot, Anusha, for coming back and then giving a very wide perspective. And I simply like the last 3 slides exceptionally well of why we are doing something. So the element of why is something is very connected to me, and I always tell as part of my interaction with class. So I'm very happy to see that it has come from your mouth, so that it will appeal a lot to your alumni and juniors now. And obviously connecting the dots, and the last one is we should cherish what we are doing. That sums up. I think that's why probably you could meander through a lot of disciplines, lot of examples, right from pickles and shampoos and jam bottles to bioenergy. You have come. Thanks a lot, and thanks to all the students for coming forward for this Alumni G-Meet sessions. Thanks, Anusha.
Thank you so much, sir. Thank you so much for this opportunity. And as I said, it doesn't feel like it's been 10 years, but yeah, I think I'm one of the older alums now. So feel free to get in touch with me. So all the juniors out there, feel free to get in touch with me on LinkedIn or send me an email. We are always there to help you guys out. So if I can't help you, I'll put you in touch with someone who can. Thank you for hearing me out on a Sunday evening. So
Yes.
yeah.
Thank you. I'm just stopping the recording. Yeah.